Stanford University.
Welcome. My name is Andy Freeman. This is the second week of EE380 2008-9 fall quarter. Next week, Ted Selker from MIT's Media Lab, which, by the way, has fantastic branding, will be talking about new models for technology business development. The week after will be Jane McGonigal, who's talking about a massive multiplayer game that has a prediction market angle. And continue with the MIT theme, Carl Hewitt, who is vacationing here, avoiding the winters in Massachusetts, will talk about cloud computing and privacy. What could go right? The week after is currently unknown. Then Guido von Rossum from Google will talk to us about Google's App Engine. So you have plenty of time to develop your web app that's going to take over the world. It's only 3 weeks away, and it really is a nice development environment. Today is Richard Kaufmann from HP talking to us about how servers, again, it's a server talk like last week, except for this time it's not so much about managing computation and guaranteeing that you're getting the computation you're paying for, but how do you actually make it all work? How do you make the power work in something closer to what we consider commodity PCs, but they're not really, and how you satisfy the fact that you cannot pump in infinite electrons into a data center. And this week I will try and do a better job of cutting us off at 5:30 as far as the tape is concerned. Thank you.
Hi, I've been a fan of this colloquium for a long time, watching it at home. And I think I just violated the GPS rule. Great. So it's not 1008, it's 2008, but the copyright notice is correct, so that's good. And I'm allowed to talk, but I'm not allowed to make commitments for HP. So there. So I thought it would be interesting to help explain how server designers think. And so this is, hopefully it won't take till 5:30, but this is a way that we're, spend some time and try and explain what goes through the mind of a server designer as that person is looking at what's happening to technology, what's happening to users, and what's happening to data centers. And so it kind of boils down to, look at server use cases. We'll talk about those in a bit. And then try and figure out what's going on with some of the technology trends that affect the designs, figure out the whole system, look for some opportunities to do something smarter than the other companies are doing, and then go back to the beginning. So the most important thing you can do, and something that I'm actually in the middle of right now, is figuring out workloads. So what do people actually want? Because if you design a server and it doesn't match what applications are out there, you've done something spectacularly stupid. And so I could fill in more detail on those, but I thought I'd just expand out the high-performance computing node. And a lot of them boil down to 2 quad-core parts, 2 gigabytes of memory per core, 95-watt SKUs, inside the beltway jokes, but basically 95-watt processors, 1 8x PCI Express slot so they can shove some nice interconnect in for InfiniBand. And these customers typically are running a parallel calculation with a time to complete job, and they care a fair bit about one server staying up for the entire run. They do a calculation for checkpoint restart so that every once in a while they'll stop the computation, spit some stuff out to disks, and then keep on going. But for the most part, if you could save $1 a server and make it less reliable, they're not interested in that trade-off. There's another set of customers up towards the top of that list that would do that in a minute. Oh, by the way, throw questions in the middle. You don't have to wait. Okay, and so these requirements drive the designs. One thing is that I use the word herd mentality, but it's kind of like everybody's afraid to leave 2-socket servers behind. It's been a nice little sweet spot, and it doesn't matter that a 1-socket server of today looks more like a 2-socket server of a couple years ago. People still want 2-socket servers, and by the look, when I said it looks like it, a couple years ago you got a dual-core part. So a pair of dual cores is a quad-core part. Memory bandwidth is about half of what it is today. Well, today they want 2 faster quad-core parts and with more memory bandwidth. So why did they do that? Because they perceive everybody else is doing that, and that's how they're marching along. Or maybe it's because that's what we just keep on making, and it's the only thing they can buy. Somewhere in the middle. Memory per socket, and socket is just a standard term for that thing that's a processor. We used to call them CPUs, but then when things got multi-core, everybody got confused. And so memory per socket is going up for most applications. Sometimes it's not going up linearly with the number of cores. Sometimes it is. And if you look at a typical Rackmount server, it's got a lot of slots. And if you looked in a typical data center, it has a lot of empty slots. People typically don't add that many expansion cards, PCI Express cards anymore. And especially if you can get nice silicon that you can glue down to a motherboard, you save a lot of money on connectors. We're getting down into kind of the details, but that's the life. So if you glue down NICs, you don't need slots so many. And the one difference are people who plug GPUs into servers, they need slots, but that's the least of their problems. We're going to talk about that in a bit. And then there's a bunch of other stuff involving storage, how many drives they want per server, whether they want big ones or little ones, whether they want them rated or just a bunch of disks, all sorts of detailed questions.
Can I ask a question?
Yeah.
So you talked about memory capacity. Can you talk about bandwidth at some point and
Yeah.
with the capacity ratios and stuff like that?
Sure. I'll talk about ratios more in terms of interconnects, mostly because when you put together a server with a processor from Intel or AMD, the memory bandwidth is what it is. There's not too many opportunities there are lots of opportunities to mess it up, not so many opportunities to make it better.
How balanced is what it is? I mean, are you compute limited or memory bandwidth limited, or is it balanced?
Since I know who you are, you're totally memory bandwidth limited. But if I were talking to somebody else, they would be completely compute limited. How's that for an answer? Okay. Yeah. Yeah. So then the other question is, so I just bought a shiny new server. Where the heck am I going to put it? It's not in your office because they're really noisy, offensive beasts, right? So you put them in these co-location centers. And when you go around and you figure out what most data centers can deal with, the old ones are at 5 kilowatts. The new shiny ones typically are at 10 kilowatts. Then this is per standard rack, which is 24 inches wide. Standard rack. And the ones that the other guys have are more than 10 kilowatts, but you can never actually find one. So 10 kilowatts is pretty standard. And the PUE, which is a efficiency metric, which means take the total number of total watts that you're using to power your data center and figure out how many of those watts are actually doing something you care about and divide. And it used to be that PUEs were terrible. These days, if you have a PUE of about 1.3, you brag about it. And if you have a PUE of 2 and above, you haven't calculated it, right? You just lie. You just say, oh, we don't know what ours is. And the high-performance computing customers are kind of different than this. They will routinely put in clusters with 30-plus kilowatts a rack. And they're willing to kind of break the rules and build custom data centers because there are advantages to having increased density for them. And so in 2011, 3 scenarios of things that might be interesting in the future. I do not know which of these will turn out to be true, and they're not mutually exclusive. So the first scenario is that we're going to get to above 50 kilowatts for a standard rack and still air cool it. Second scenario is that the heck with data centers, we're going to have trailer parks. So we're going to put all the servers into standard 40-foot shipping containers, put batteries in there. These are places that humans will never go. Just make them as offensive as you can. Put all this junk into a container, close the doors, water goes in, power goes in, little thin fibers come out for data. That's it. And extremely dense containers is one option. And another option which is emerging is, and you might have seen a news report from Intel talking about something they did in their Rio Rancho facility, where they said, well, what if we kind of break our own rules and let servers run really hot and just take in outside air? Yeah, we might break a few more servers, but maybe it'll pay for itself over time. Now we're starting to get a theme, which is not being so emotionally attached to one particular server, but being attached to the total cost of computation, right? And that'll be a recurring theme.
So can I ask you a little bit PUE, so cooling is overhead in this case?
Yes, cooling is overhead. And
AC/DC converters are overhead?
right, so not necessarily AC/DC, but cooling, UPSs, which in the old days did 2 conversions, but these days don't. And the lights. Okay, so the other thing you need to look at is how emotionally attached are people to nodes. So do you design them with redundant power supplies and fans? That adds money, and if you do it wrong, it adds power consumption. Do people want the ability to swap hard disks in and out? This must sound like really silly, basic stuff, right? But I get into incredible fights over spending 50 cents on a server, and it's all of this stuff. So this is kind of the real world. It may not be a good world, but it's the real world. Then other applications want the absolute cheapest node possible, and they're willing to accept failures, and to a certain extent, they're willing to accept wrong answers, right? And that was something that at least my old brain had trouble getting around. But then somebody asked me exactly how much do you care about the 5th result on a search page? What if it... Exactly. But what if it was wrong and you hit refresh and you got something different? You'd say, oh boy, the index got updated. You never know.
I still didn't get my clicks, so I got a lot.
Right. But class of application where absolute perfect answers aren't worth it financially.
What do you mean by a wrong answer? How does it manifest in doing something?
Maybe you would miss a link. So you would miss a search result.
No, that's from the user point of view, but from the server point of view, what is it doing?
2 plus 2 equals 4. Equals 5. Or
If that's in the kernel, it can cause you to crash the next machine unless the machines guard against each other.
so you might have seen something from Amazon where they talked about how their system health monitoring algorithm had a problem, and that machines crashed their neighbors. We're going to get to that theme, which is that signing up for these less accurate servers means spending a lot of time and money and love on the software to make sure that you protect against that. Yes?
So have you noticed a difference in terms of these requirements, between people who are vertically integrated? So Google controls everything, from hardware all the way to the last bit of software that runs, versus somebody who is buying something from HP, running, Microsoft, OSs, then putting some other application from third parties, and then they're paranoid about reliability because they cannot do end-to-end
Right.
at the application level.
So a specific thing, which is that even though a whole bunch of my friends work there, Google's a black hole. So I don't know them. I know them socially, I just don't know them, right? But if you have complete, and there are some folks who you can imagine might do something called self-assembly. And actually Chuck Thacker was here last year talking about self-assembly in containers. Really interesting talk. And maybe you don't need companies like us to do something. And if anybody's watching this on the web, don't fire me. But maybe you can get rid of all the middlemen and just build your own software, build your own hardware, and do it all yourself. Luckily, that turns out to not be a good idea for almost everybody. Does that answer your question?
Kind of. I can take this offline. That's fine.
Okay. So, so the trend is that folks, just like the same way that folks figured out how to parallelize their applications so they didn't need big, 64 socket servers anymore, and they could do more with clusters of 2-socket servers, folks are also figuring out that they can save money if they can use less expensive, less reliable hardware. And if your application's amenable to it, that's something that they're willing to do. So part of this is that you can get too enthusiastic about the capabilities to actually do that kind of software. You can easily get too enthusiastic about it. So it's hard. And for example, cloud file services typically use replication, so they'll make 3 or 4 copies of a file instead of using RAID. And so that saves money on RAID. You pay a little more for disk. But for some applications, it just doesn't work. Okay, just a general point. Okay, and the other thing is that because it's a very horizontal industry, innovation is pretty constrained. So Intel drops a new processor, everybody has to beat time to market with that new processor, because if you miss that by a couple of months, you've lost money. Memory comes from a certain number of people. It's all with a standard interface. And as a recovering high-performance computing person, that just it drove me crazy, because there's so many optimizations that you could do if you could break that silly memory interface between the processor and the memory. Forget about it. Just economically not viable. So the mainstream technology steamrollers outliers. Always has, and perhaps it will continue to do so. And the other way I think of it is, being different means that you're always one mistake away from being dead. Standard thing. Everybody says Ethernet will win, right? But Infiniband is cheaper per bit per second than Ethernet. And it's winning in a lot of markets. But everybody thinks eventually Ethernet will win. If you don't make me say when, I'll agree with it. Okay, picture of my PC. So that's typical air-cooled PC for 2006. I think broke in 2007, so it's an old picture. Now, if you want to know why your power bill is going up, look at a gaming machine. And I usually give this slide to older crowds, and so I said, blame your kids, right? But 3 225-watt GPUs, and that's before you overclock it. And 120-watt CPUs, again, before you overclock it. And please, I hope nobody in here does stuff with liquid nitrogen. And then 60 watts for disks and memory. And because it's not your power bill, you go and get the cheapest power supply you can get, which is less than 80% efficient. You're over a kilowatt when you're playing a game or when you're folding. So those things are, that's just craziness. Okay, so if things keep on going the way they're doing, that's actually a Van der Graaf generator, but you can imagine that might be a heatsink in 2014, right? And there's a roadmap that said that a chip interconnect would be 10 kilowatts. in that time frame. And it obviously won't happen, so something has to change. Okay, so the other thing is just how clever can you be to make things more efficient? So this PUE, remember the ratio of all the power you use and how much power is useful. 5 years ago, 2 and 3 was sort of a good number, and 5 was pretty, happened a fair bit. Today, 1.5 is good, 1.3 is great.
Google
Right?
says they're 1.2 across all their data centers.
1.2 is really, really good. Containers can potentially get under that. UPS efficiency, so uninterruptible power supply efficiency, 5 years ago was 94%, and that was because they were converting once to come into the battery and once to leave the battery. Now they just bypass the battery if everything is working okay. And so that's gone from 94% to 99%. Power supply efficiency 5 years ago was 75% on a good day. These days, 92% is sort of expected, and there are a bunch of standards that are sort of marching everybody to a certain efficiency level at load. And the other one is fan power. So per 2-socket node, we used to routinely blow 60 watts worth of fans and just have them on all the time. And now 5 to 10 watts, 5 watts at idle, perhaps 10 watts at a reasonable load.
For your power supply efficiency, are you counting both the loss in the box power supply and then also in the power supply that sits right next to the CPU and converts down to the CPU core voltage?
No, just the power
the
supply box. But the voltage regulator modules are actually getting pretty efficient too.
And then,
Maybe a bit of an irrelevant question, but to do with power supplies, do you come across places that have problems with harmonics being generated by large numbers of switching power supplies going, kind of getting all in step? And
Not a power supply engineer, so outside my realm of expertise. Yeah.
is this 92% at peak utilization, all utilization, points of the server?
Good question. And so it's generally at peak, but the specifications are actually pretty nuanced, and they say at 10% load, 50% load, 100% load, what the percentages are. And you can kind of design trade-offs, and so that the curves are actually getting remarkably flat.
Okay.
Oops. Okay, so this is something that's also obvious but hasn't been in the past, which is that when you buy a server cluster, when you buy a cluster, you should really look at what it's going to cost you for some number of years of operating it. And the numbers range from 3 years to 5 years, depending on how much you like to hold on to things. And so if there's ways to spend more money on things that are more efficient, it can make sense. Now, quite often, and universities are notorious for this, is that they'll buy things based only on initial purchase price, right? And so you come in with the cheapest option, you win. You come in with the tasteful options, you lose. Now, blades, which sort of spend a lot of time on efficiency of a group of servers, both power efficiency and human efficiency, are all about this TCO calculation and not so much about initial purchase price. So they're more expensive up front, but they pay for themselves for certain applications, typically enterprise applications. And so let's go to that one example. So this is, I just picked this from HP, but I did this about 6 months ago. So you can, in one of our 1U little servers, you can either pay a base price or you can upsell yourself for an extra $200 list price to get a more efficient power supply. So I used the numbers from Luis Barroso's paper from Google just to say, okay, so for a 400-watt load, which would be a typical high-performance computing class server, you would save $500 over the 3-year life of that server if you spend the extra $200 up front. So your net savings would be $500. Many customers will not buy that option because it changes the initial purchase price the wrong way. Okay, other things, reason why blades can make sense. For example, and this goes back to your point about when you run power supplies, how efficient are they when they're at half load? Typical rack-mount servers with redundant power supplies, if you're running your server at 100% load, both power supplies are running at 50%. So you're not in a good spot on the efficiency curve. Blade systems, at least ours, but I would assume other folks can do this, is that they will run as many supplies as is necessary to power the load, and the other ones are in hot standby. And so in one AC cycle, they can bring those on if they're needed. If another power supply fails, or if somebody's running LinPack and all of a sudden the power draw goes up. The other things that people do in blades is that they've got very nice fan designs, and there's sort of a clean sheet of paper. You're no longer in this one-use space. By the way, one-use servers are kind of interesting because the herd all loves one-use servers, but those tiny little fans are pretty inefficient. All right, so kind of open your mind a little bit. Don't think everything has to be in one U. Okay, so and just from this was like a year and a half ago, we figured out that all the stuff that we did in blades typically saved us 25% of the power bill compared to a one-U server.
So
Yeah.
if I open up one of these data centers in a box, like container thing, do I find something much more exotic than this stuff, or is it just packaged up really nicely?
You can find stuff that's more exotic than this, or not. So our blades, we have a container called a pod, and our blades go in there, but our container's made up of standard 19-inch racks, and so you can put other stuff in there as well. One-use servers if you need to. Actually, it's a good thing to be able to put some one-use stuff in there, like the top of rack network switches and power distribution units. There's this whole wonderful ecosystem of stuff that plugs into a rack. But typically, you will not find one-use servers, just because if you're getting into containers, you care about efficiency, and you want to look at a different way of doing that.
So you still have individual power supplies per server, or you do DC in the whole rack or in the whole box?
It's an interesting question what the right level of aggregation is for power supplies, and it's not necessarily the right answer to go as high as you can. But you would prefer not to have one power supply per server. Okay, so it can change a lot depending on what design you're talking about. One is almost always a bad answer. Okay, so I'm going to go over these next slides really quickly because it's just basically saying what everybody knows, which is that nobody's getting single thread performance boosts anymore. They're just getting more cores. And the other thing is that it's two reasons. One is that just the power went nuts when people tried to turn the speed crank. And the second one is cores got so complicated that they became unmanageable as a human effort. Intel, this is their numbers going from a single core to a dual core part. And basically this slide says that if you overclock a CPU, you're jacking up your power by 73% and you're only getting a 13% application improvement for some reasonable set of applications. So gamers at home, overclocking the processor know what you're doing. On the right, when you went dual core, you actually lowered the frequency by 20% to keep the power envelope the same, and you got 73% more application performance. So those two curves just flipped. Murray McLaren from HP Labs. This slide is making its way around the world. This is a good model for what the world is. So 2007 quad core, 2011 16 core, 2015 more cores than you know what to do with. And the problem is that it's very hard to go against the herd. So the herd is all bought into that model of just add more cores. And so we talked about this before. It's hard to do anything different. The problem is that your program doesn't necessarily run faster. So you have to rethink algorithms and down to the simple level of don't even think about just assuming that if you run the same binary, these things will work as fast, because there's all sorts of compromises and changes that are getting made to microarchitecture designs that they make it so you really need to recompile to get decent performance. And this is just flame bait. So why are we stuck in this world? You guys mess up? Transactional memory is sure interesting, but it's not taking over the world yet. So plotting the herd, dual core was universal in 2006, quad core 2007 to 2008. There's actually a 6-core part out now, but no one will ever hear about it because it's in the expensive 4-socket server space. Intel part named Dunnington. I'm sure their marketing department has a better name for it by now, but I know it as Dunnington. 8 cores coming real soon, and 16 is an open discussion. And yeah, everybody's been here before, starting with the Cray 6600 I/O processor. But the herd hasn't been here before. So mainstream is coming in and starting to experience this. So I think I'm going to retire hearing around 3 gigahertz, right? Which will be the speed of a standard x86 core. You're just going to hear that a lot, and actually the number is more likely to go down than up for a long time. And there are some ideas. Norm Jopi had posited the idea of, well, maybe you should put a couple of fast cores on the chip that consume more power, but the scalar part of the program maybe should run there, the stuff where single thread performance really matters. So that's one possibility, but there really aren't that many creative ideas for what to do other than just put more cores down. We'll talk about some things later when we get to acceleration. One thing that they can do is they can put a lot more floating point units down, and there are 16 eyes in wide, which is an interesting number. But if you're going to do a teraflop chip, you really need wide floating point units, otherwise the thing's impractical. So that's a single socket teraflop processor. The other thing to recognize is that just because you have a problem doesn't mean everybody else has a problem. So if you're DreamWorks and you're rendering a movie, everything is just sunbeams and unicorns, right? You're rendering a movie, you dispatch one frame to every core that you have in the machine room, and so what if it takes 45 minutes to run? Nobody cares because the only thing you care about is frames per second aggregate over your whole cluster. But once you solve their problem, and they leave the room happy, everybody else who's left is mad at you still. So, still a problem. Okay, other things. There are different sorts of processors. The whole world is not x86, and even within x86, the Intel marketing department doesn't call them this, but they're expensive parts that are intended for servers that are more than 2-socket. There are mid-range part for the 2-socket servers. And there's a variant of that that's more expensive but lower voltage. And cloud customers, so cloud computing customers, are merciless accountants, and they'll figure out, based on the cost of power for their data center, whether it makes sense to pay more to cherry pick the chips that run at a lower voltage. Okay. Itanium still has a place, and it's for larger than 4-socket servers, and for applications where reliability, availability, and serviceability are very important. And there's other stuff, lots of really interesting stuff, but at least for a company like HP, a non-x86 ecosystem is a real problem for scale-out computing. It's hard to be different. And then there's people using gate arrays, graphics cards, and other custom ASICs. And some of that technology is breaking into the real world, especially if you're in the oil and gas business. GPUs are very interesting, and there are ISV applications that actually use them. So some of this is getting real. There's enough gray hair in the room to remember when memory was 1 cycle away from a processor. It was a wonderful time. And it kind of got worse, and it got twice as far away every 18 months until now. There's good news with multi-core, which is that when you're always going to hear around 3 gigahertz, you're always around 195, 200 clocks away from the processor. So memory latency isn't getting worse. Isn't that wonderful? So memory latency is not getting worse. Memory bandwidth is getting worse fast. You still need to track Moore's law or aggregate performance in order to keep up. But it sure is going to require a lot of innovation of the processor to memory connection. Now, the interesting thing is that the next generation Intel part gives you a one-time gift from the heavens. It's going to give you a lot more memory bandwidth. But it's a one-time gift. And those of you who remember Alpha remember that EV7 did the same thing. A one-time gift from the heavens, more memory bandwidth than you know what to do with. Just wait 18 months. They're going to double the number of cores. You're going to be back in the muck again of not having enough memory bandwidth. I'm speaking to you. Okay. Also I/O. In Infiniband, they went from single data rate to double data rate. No extra points for figuring out that the one after that's quad data rate. The one after that's not called octal data rate. Just for information. Ethernet, the transition from 1 gig to 10 gig is happening slower than anybody thought it would. But it is happening mostly at the top of a rack as an aggregation technique. But you'll start to see nodes. One of our blades now has a glued down 10 gigabit Ethernet NIC on it. It's a large memory AMD blade. And so I think you'll see that as a trend going forward, where you see more 10 gig at the node level. But it's taken a long time to get there. And then PCI Express has gone through multiple doublings. And PCI Express Gen 2 is becoming ubiquitous over the next. It's already there in desktops. It's there in some servers and will be there in all servers within a year or two. Just doubles the data rate. Gen 3 doubles the effective data rate, 2-3 years later. So the I/O stuff is kind of happening at its regular pace, and it's there to enable interconnects. Quad data rate, for example, really relies on PCI Express Gen 2 in order to get full bandwidth. So again, it's an ecosystem. There's no reason to have a faster I/O slot if there are no adapters for it. I can't believe I'm saying something so obvious to this crowd, but it's amazing how often the mistake gets made where you have too fast of a NIC for the computers that are out or too fast of a computer for the NICs that are out. Everybody's got to go in lockstep.
You mentioned one-time gift from next-gen Intel part about memory bandwidth.
Right.
How much memory bandwidth are we talking about?
Because it's kind of a semi-announced part, I don't feel comfortable. But remember that Opteron went from a traditional design with a common chip between the processor and the memories to one where the memory was hanging off of each processor. Intel does that with this next generation and gets a integer multiplier of memory bandwidth per socket compared to where they are now. And it's an integer greater than 1. Okay. So single thread performance really matters. The x86 core speed will just keep on careening around 3 gigahertz, more than you want to know. And I keep on thinking that compilers have to save the day, right? Which is that you really want the compiler to automatically parallelize at least within a socket, just within a socket. If you could just figure out how to use a socket's worth of cores, that would keep compiler writers employed. Speaking as a former compiler person, that's a good thing. And it would keep people writing applications so that they could actually take advantage of these chips. I don't see it happening.
So for the benefit of the younger generation, you said there once again. When was the previous time?
Oh, RISC. RISC stands for relegate the important stuff to the compiler. And EPIC, which was Itanium for the wide word stuff, expect perfectly intuitive compilers. Okay. And if any of my Itanium friends are listening to this, don't kill me either. Okay, so so desktop and gaming has a lot to do with the future. And again, I just got reminded that desktops are so, last year. Yeah, now it's notebooks, but gamers are important. And they're getting forced to adopt parallelism. The really fast graphics card these days actually have 2 GPUs on them. And they've used multiple of these. So they're starting to realize that parallelism is important, not just within a GPU, but across GPUs. So interesting stuff is happening there. And also the convergence of multi-core and accelerators is happening. That's Fusion from AMD and Larrabee from Intel, where they're looking at taking GPU technology and bringing it, at least x86 technology, in Intel's case, goes to a graphics card. Okay, so let's do a little extrapolation. So let's assume we're going to get a teraflop in a socket in 2013. Maybe that's accurate. We just assume Morse cores hold. Here's how the math of the mainstream works. You're going to get 100-ish gigaflops the end of 09-ish, right? I get really fuzzy on dates where you might remember this, in '09. And when we're talking about 2011 and 12, I know you won't remember it. Or I'll be, raising oranges someplace. So anyway, 200 gigaflops, first half of 11, 400 gigaflops, end of 2012. And so that's where the mainstream will be. Now, these mainstream parts will have, sort of the regular, march of improving memory bandwidth and I/O bandwidth. And memory bandwidth will always be about half of what high-performance computing applications want, and it'll always be more than what cloud computing folks will want, for example, in search applications. Right? That's why they're called mainstream parts, is that they're the average of what everybody wants, not what you want. Now, what happens if acceleration really takes off? It sort of kind of breaks this mainstream rule. Hasn't happened yet in the entire history of computing, but maybe it will. So accelerators are over-provisioned in some dimension. And so GPUs are over-provisioned in the number of floating point units that they have. FPGAs have more functional units than are available in mainstream parts. So they all change a rule somehow. And if you kind of look at it, you kind of expect somewhere between a 2x and a 4x multiplier over a mainstream part. So if we're in that 400 gigaflop era in the end of 11, then we would be at somewhere around a teraflop with some kind of accelerated chip. Now, Intel's Larrabee, NVIDIA with CUDA, AMD with their close to metal stuff. These are all examples of accelerators that are aiming after that space. One interesting little note is that you can trade off memory bandwidth in exchange for capacity. So graphics cards typically have, 512 megabytes for a big one, but they have a lot of bandwidth.
They're up to 2 gigs and 4 gigs now.
Right. Those are the ones that you can't afford.
Yeah.
Okay. So acceleration gives you a lot. GPUs have been on a faster growth curve. Larrabee has an interesting potential in that it's an x86 instruction set architecture, which means that you might be able to do something really nice with that. A general complaint about accelerators is you're not an accelerator person unless you claim that you're 50 times faster on something, right? Problem is you're not 50 times faster on an application. You're 50 times faster on one little loop in one corner of the application. General rule, the people in the room who are much better at this than I am, but FPGAs generally work best when numbers are small and when data paths are really wide. So very highly parallel data flow. Then the problems are that if you want to do 64-bit full IEEE math, those FPGAs become a little less endearing. That might change because FPGAs are also on a steeper growth curve than mainstream processors. Another problem that's really hard is that reliability at scale is a problem. So large clusters are particle detectors, right? They'll get a particle strike, and in an FPGA, not only will you take out some data, you'll take out some of your logic. Then you're really messed up. So if you're thinking like a high-performance computing person, you just realize that you're dead. And if you're thinking like a cloud person, maybe you're thinking just one little part of you is dead. But it's a problem, and designing around it involves replication. There's some stuff that's done on rad hard gates that might be interesting and might help some of the math, but you have a real problem. And the other one is programmability. So they're just a pain.
So which languages and operating systems?
Sorry?
So which languages and operating systems?
For accelerators?
For general programmability, in your opinion.
So the high-performance computing crowd is Linux, with Windows becoming acceptable for some of the user base. Cloud computing is cloud computing is a mixture of Linux and Windows. And in terms of languages, it's a lot of the boring stuff, C and C++, with a smattering of things like Erlang. So revenge of Prolog, right?
Fortran finally died?
Fortran is incredibly popular in the high-performance computing community. One problem is that the practitioners of it are getting old. But it's amazingly effective.
It's just you didn't say the word Fortran.
I didn't say the word Fortran. Part of it is that I sort of got bored into this cloud computing stuff, and so I've been forced to forget some things that I knew about high-performance computing. Okay, memory system. This is the slide that makes high-performance computing people's blood boil, which is that people do Herculean efforts to improve memory bandwidth, but processors get faster more quickly than memory systems get faster. And so memory is not only, has traditionally been farther away in terms of cycles, but the straw gets narrower and narrower. Fully buffered DIMMs were an attempt to fix this. And the idea was that if you traded a little more latency and a little more power consumption, turned out to be 2x power consumption for memory, you'd get a lot more bandwidth per pin, and so you could have both more bandwidth and a lower pin count. Then this last thing is buffers on board, BOBs. And the idea is that you run a very fast link between the processor and an intermediate chip, and then you use traditional memory from that BOB. And that's a design that you will see in the high socket count servers over time, but is kind of a one-time attempt to greatly increase memory capacity. Now, you're going to need to use an optical link to really fix this, and I've been showing this slide for a year or two, and it always says 5 years.
5+.
Yeah. That was just because I got honest at one point. But it's a while away. Okay, chipsets. So we talked about this a little bit in terms of north bridges and south bridges. They're kind of getting boring, and that's because when the memory system gets slurped into the processor itself, chipsets become just things that take some kind of an interface like the QPI bus from Intel or HyperTransport from AMD and make PCI Express lanes out of it. And so it just comes down to kind of a boring conversation about how many, what kind of PCI Express slot lane do you have and how many lanes do you have? It kind of boils down to it. There are some improvements in PCI Express Gen 3 that allow I/O devices to be more equal participants with the processors in the coherency mechanism. And that'll be useful for some NICs and some other stuff. And the other thing, which we'll talk about why this matters in a little bit, the 2008, so the current processors and chipsets out of Intel, they did something interesting. One is that they have a sped up frontside bus with PCI Express Gen 2 for their workstation part that's also in some servers. And then their low power part, San Clemente, has a design center around low power, and that just by mistake, they made it so that it had really good performance. So instead of fully buffered DIMMs, they use DDR2 memory and DDR3, DDR2, and they wound up reducing bandwidth in a way that didn't matter and reducing latency in a way that really did matter. And so the end result is that performance is about the same at a lot lower power consumption. So we've had an interesting mid-cycle refresh of putting out San Clemente servers just because their performance per watt's been so good. Okay, so here's a San Clemente server. So instead of big old FBD sites, there's 4 memory slots per server. These servers sandwich together. So in the space where you used to get 1 2-socket server, you now get 2 2-socket servers. And lots of gory details. The slides are on the website. But we can make a 12 teraflop rack out of this. And if you look at the performance per watt, so this is putting several things from the talk together. So remember, we spent a lot of time talking about how blades, and this is a blade system, get you better power efficiency. And then we talked a little bit about how Intel's chipset really helped a lot. You put those two together, and you get something that's within spitting distance of Blue Gene in terms of performance per watt. But remember that Blue Gene's a LinPack machine. It's good at dense linear algebra. But in the real world, things aren't that nice. And so when you get extra memory bandwidth, and we talked about how even the memory bandwidth on the x86 line is going to get even better, you wind up with a really interesting performer. So this is an example of why you don't want to fight the mainstream so much. You put technology from several different places together, and you get something pretty compelling, and everybody only had to work on their part. Okay, this is a Tata cluster made up of those blades. Actually, it's not the double dense blades that they selected, it was the full-size blades. And this is a very large cluster. When it came out, it was number 4, I think, in the world. I can't even remember anymore. And it got put together in 3 months. It used to be that for a machine of that size, you would have had to install it for months and months and months and months. So things are getting kind of interesting. We were talking about data center design. These things peak out at more than 32 kilowatts a rack when they're running HPC applications. And so they've done an interesting thing. Servers are traditionally designed with front to back cooling. Cold air comes in the front, hot air comes out the back. What they did to avoid mixing is they put in a drop ceiling right in the middle of the racks. And so you have a ring, concentric rings, of hot and cold. So pretty clever. And an example of, you don't have to go to liquid cooling to get very power dense racks. If you're willing to build a custom data center, and trust me, you can afford the data center for what these servers cost, you can do something pretty interesting. Okay, and so if that was the big, here's the baby version. So that's one little 6U rack that holds 8 of those 8 big 2-socket servers or 16 little 2-socket servers. And we even sell a little kit so you can turn it on its side and have it in your office, except it's too noisy. So you want this in your neighbor's office, or you want it in the hallway, or you want it in the closet someplace. But it's kind of a personal cluster. And this is an area where Microsoft is really focused on their HPC clustering software. They're looking at engineering applications, for example, where you want some shared computing resource someplace, but you don't want to buy into the whole big cluster idea. You just get one of these things and throw it in a closet.
This is a closet with good air conditioning.
It's a closet with good air conditioning, indeed. Okay, we talked about blades, but rack-mounted servers are useful for some things, and they're useful for very large memory capacity servers. They're useful for high socket count servers when people want lots of storage. So people can get really excited about the new shiny stuff, which is blades and non-traditional form factor servers. But the good old, solid, reliable rack mount servers certainly have their place. They will have their place for as long as I care to track. And part of the reason is that they'll always be useful as head nodes, where you want to have some number of the nodes in a cluster there you can configure lots of extra stuff. So, interconnects. Here's a real problem, which is that if you look at floating point applications, and the same kind of math extends out to other applications as well, the bandwidth per node is somewhere between 1/100th and 1 byte per peak flop. And that's a huge spread. There are subtleties involving whether you then have further chokes in the network, depending on whether you have a tree or a torus or a mesh or whatever. But if you're looking at a teraflop chip, that means that you need either something like a tin can, two tin cans in a string, to an interconnect that's 1 terabyte a second, right? Which is impractical in today's technology. So latency in general, 5 microseconds is good for a lot of folks. 1 microsecond is a lot better, and Infiniband is basically at the 1 microsecond level. That's user process to user process. So that's running MPI. Latency is about a microsecond these days. And the other requirement that customers have is that all they care about is dollars per bytes per second. So they want the cheapest possible interconnect they can get for a given bandwidth. So we sort of already mentioned this, that Ethernet always wins. But if you look at the cost of a NIC, the cable, and your percentage of the switching structure, Infiniband is a lot less expensive. There's still room for proprietary interconnects. The Cray XT3 is an example. But it's a hard row to hoe, and you better be delivering a lot. So you're in that kind of one mistake away from oblivion category. Infiniband is maybe 2 mistakes away from oblivion. Talk a little bit about Infiniband. The mainstream part these days is DDR, double data rate. And let me show you something that has changed the way people put clusters together a lot. And these are these optical electrical cables, EOE cables. And their cost breaks even at 10 meters. So folks use them for the long links in clusters now. And they're amazingly effective. So the rest of this slide just kind of goes on to say that quad data rate's coming soon, and I don't know when soon is. Infiniband continues to have cost benefits over 10 gigabit Ethernet, and that's partially just for as long as the Ethernet switch suppliers like their high prices. And so the takeaway is Infiniband is good, but Ethernet is always ready to gobble you if you screw up. So if we look at today's parts and we look at the range of requirements, we get anywhere between 1 gig-E and 1,000 gig-E of the length that we would like. And the rule of thumb is that there's no rule of thumb. Applications spread around this all over the place. But there's a lot more money in terms of revenue at the 0.001 bytes per flop area than there is at the 1.0 bytes per flop area. So if you spend a lot of time working on that 1 byte a flop interconnect, the air doesn't have a lot of oxygen. And so, what you'd ideally like to be able to do is that you won't burden the cost of the base server with the desire to have more bandwidth, but you can buy your way into it. The standard joke is that we want customers to run out of money before we run out of slots. But that's not really true for interconnects. They really kind of pervade the system, and it's hard to build a server that gives you all the interconnect bandwidth that you would like without affecting the cost of the base unit. Cheap slide, optics will eventually replace copper, right? Who cares that anybody ever says that unless they tell you the exact date. Optics is currently a win for 10 meters and greater. There's lots of reasons why optics will eventually win. It's kind of hard to get anybody to go much above 10 gigabits a second for a link on copper that goes any real distance. And the copper is nasty cables, but people will put up with nastiness if it saves them money. And copper also consumes a lot of power per unit of distance compared to optics. So these are these EOE cables. That's a 20 gigabit per second bidirectional cable. And if I was showing you that, it used to be an Intel part. Intel sent me one so I could take it to somebody to show them. And it was about a 5-pound thing for a 100-meter cable. The equivalent copper cable I couldn't lift and my car couldn't carry. I have a small car, but my car couldn't carry it. So petaflops. So the petaflop apple has been picked from the tree, and there's a Lano machine that was done with IBM and AMD, and IBM with the cell processor that's a hybrid petaflop top 500 machine. So it's a Linpack Marvel, wonderful thing. Now, let's say that a mainstream part's going to have a teraflop chip on a package, some combination of accelerators and general purpose processors. The challenges we've talked about before is what are the ratios? The memory bandwidth ratio is going to be like the interconnect ratio bandwidths. And there are 2 partial answers to it. Intel had a program called RMS, Recognition, Mining, and Synthesis, which was essentially, I have a solution, let's go find some problems. So I have a chip that has kind of ratios that are skewed a lot more towards flops and away from bandwidth. What can I do with that chip? The other one is perhaps just let the software guys figure it out. They'll figure out how to use it. That won't necessarily work very well. There's another issue that has to do when you talked about operating systems folks want to use. If you're trying to build a parallel cluster where you care about time to completion, so they're tightly coupled, any kind of jitter that's caused by an operating system quickly cascades and becomes a problem. And so there's a lot of work being done on either quieting Linux or making an embedded kernel more like Linux in terms of its capability. And I think by the time that everybody gets done, those two things will converge and you won't know which one won. So let's look at a petaflop, a sustained petaflop, and that means sustained on a real application. And so depending on how much you're accelerating things, here I'm assuming a teraflop chip, but remember I'm breaking a lot of those ratios. I'm just assuming that I'm going to have 3% of peak floating point for useful floating point in my application. And as you go towards a more mainstream part, like a 100 gigaflop that's in the first column, I assume a 7% percentage of peak. The other thing is that I assume that you'll have an 8-socket SMP, and clusters of 4,000 servers are practical. 7,000 servers are pushing the edge. 10,000 to 20,000 servers is going beyond that. And so those are clusters of SMPs. There are other approaches that folks have used, IBM and BlueGene, where by taking other trade-offs, you can get higher, but that's for the mainstream. Now, the problem here is that assuming a fairly radical memory bandwidth, so 35 gigabytes a second of memory bandwidth per socket, your bytes per flop is 0.04, right? And so you really would like that number to be about 0.5 for mainstream applications and higher for more hardcore HPC applications. So you just broke the rule by more than a factor of 10. So you can't just assume your applications are going to run on those kinds of systems and get performance. You have to rethink them, or maybe you just have to run different applications. So again, RMS was a way of just changing the game, so go for merging application. The other one is to just fix the darn memory interface, and something, optical, stacked memory, something fixes it. But that's just wait for a miracle right now. Okay, so petaflops are boring. Exaflops are the new petaflops. And Bill was in the room with me when this first number came up. I think that everybody decided that this was too high, but it was order of a gigawatt to power an exaflop worth of cores. And there are all sorts of other problems, but the idea was if you needed a gigawatt, you can buy it. It's $4 billion, and essentially you take a nuclear power plant, strip out the control room, and put a cluster in its place. It's carbon neutral. You may not want it in your neighborhood, but it's carbon neutral. Cool. So anyway, so what we talked about is where your users are, where they're going to put their servers, figured out what kind of soft features they want, like reliability, availability, and serviceability. You need to understand technology, and then you worry about the whole system, and then you just start over. That's it. Any other questions? Yes?
So you had on your slide memory capacity plus. What do you mean by that?
So that was for fully buffered DIMMs. Because it's not a bus structure like DDR memory is, you can, by adding latency, every time you add a fully buffered DIMM chip to a server that takes FBDs, you add a couple of nanoseconds of memory latency, but you also add capacity. And it's a serial scheme, so you can keep on adding memory.
When is Intel going to get back into the memory business? There are people making money on parts that are on a motherboard that aren't named Intel.
Right. So politics I won't get into. But if you believe that stacked memory is important, then processor manufacturers have to figure out how to get memory put on top of their chips. Wow, they turned off the tape I thought it was 5:30 they turned off the tape.
Yeah, well, we can talk for as long as you want.
Great.
Watch out for trap doors.
Should I climb on the table? Yes.
You mentioned 1 microsecond latency for InfiniBand. Did that include a trip to the kernel?
Actually, so the trick is that you don't have a trip through a kernel.
Okay.
So the modern interconnects, including 10 gigabit Ethernet, have a way to do message passing with no kernel involvement. And it involves mapping a piece of the PCI Express address space into a user process.
Including the control addresses?
So think of it as the high-performance computing NICs got virtualized before the mainstream world got virtualized. Great. Thanks. Yeah. So some of the genome guys want as much memory.
For more, please visit us at stanford.edu.